Hello everyone, in this video we'll talk about Ospf. In the previous videos we saw that RIP, Routing Information Protocol, is an implementation of distance vector routing, and similarly Ospf is an implementation of link state routing. So if you remember, we had two types of routing. In distance vector routing, what we saw was uh, each uh, each router will know what is the destination, what is the cost, and what is the next hop. And in case of link state routing, we saw that each router will know the entire topology of the system, and they will construct their own routing tables. So OSPF OSPF is based on link state routing. It is an implementation of link state routing. The full form of OSPF is Open Shortest Path First. So as the name suggests, it's an open protocol, and this uses the Dijkstra's algorithm, so SPF algorithm, for finding the shortest route and things. First of all, this protocol OSPF is very much suited for very big networks, mainly because OSPF can split networks into areas. Why do we have to split networks into areas? There are many reasons. For example, let's say we have a network. Let's say the number of networks is really high. The number of nodes, number of routers in this network. We have so many networks, and they are all interconnected. They are all interconnected. Now what happens is, if one router wants to send what is the topology of the network, then we'll send LSA packets, and the things will get flooded, right? Also, Dijkstra's algorithm and all other routing algorithms get more and more complex as the number of nodes increases. So it really becomes very hard to manage all these routers if they're in a single connected system. So what OSPF does is, it can split that whole topology into areas. So let's say this is one area, this is another area, and this is another area. So now we have split the network into areas, and what we can do is, we can say these routers are the backbone routers, because once you reach this router will know what to do with the packet, whoever wants to receive it. So this can be considered like a subnet, right? Even though this whole system is an autonomous system, we can consider this as a small subnet, and we can send packets. If we want to send it here, we just have to reach here. So this backbone routers can distribute the packets to their subnetworks. So this makes it very useful for very big networks. So we have backbone routers here. All right. So this is for areas and backbone routers. Now we'll look at something called neighbors. Neighbors are something like, let's say there are two routers. Neighbors are something like friends. Let's say we'll discuss the type of packets, but let's say this is the router and this is also a router. Now if this router sends, and they both are connected, and let's say if this router sends hello message, now this router will also say hello, and they both note down they also send, along with the hello message, they also send their router ID. Router ID is mostly an IP address, so it also sends a router ID. Now what it happens is, this will note down this router ID as its neighbor. So in the next hello message that this router sends to some other routers, it will send that hello. It will send hello to here as well, and now it will say my neighbor is this router. So it can exchange messages this way, and this helps in forming the topology of the whole system. So they send hello messages, and if both routers are linked properly, then they are called neighbors. Yeah, that's it for neighbors. Now we'll look at something called designated and backup designated routers, DR and BDR. Let's say there is a system which is, let's say there are 6 routers and every router is connected. Connected this way. Okay. Yeah, we'll make a connection here also. And this router is connected to somewhere, and let's say this router is connected to somewhere, and things, they're connected everywhere. Now let's assume they all know the topology of the system and everything is working perfectly. Now suddenly this link breaks. Now this link is no longer available. Now what happens is, this router will send an update packet to all the routers nearby. Okay, and this router will receive it, and it will also now it will advertise the same thing to all other routers. It's only connected to this, and this will receive, and this will flood to all other routers. Now this will receive it, and it will also flood to all other routers. So this creates a lot of flooding, right? So what happens is, in OSPF, to prevent this, any one of the router will become the dominant router, the designated router. So now what happens is, whichever router is the designated router, only with this designated router other routers will form a one-to-one relationship. That is, only with this router they will become good neighbors. What happens is, if there is an update packet that comes, the other routers will ignore all the updates that are not from the designated router. They'll accept only the updates from designated router, so that the flooding is reduced. So designated router is more of a primary router. It controls other routers in the network. So if we redraw this diagram, let's say, now this becomes the designated router. Now even if this link dies and it sends a packet, and this will receive the packet, and then it will update other routers. Now even if this is connected and it receives a message from this router that this link is broken, this router will not acknowledge that message, because it will acknowledge only the message from designated routers. And this designated router is selected based on priority, and if priority matches, then router ID is used. Whichever has the highest router ID, that will be selected as the designated router. And these all happens automatically. There is no specified designated router. You can of course increase the priority, but this is chosen automatically. All right. And if this designated router fails, some other router will become the designated router. That is called backup designation router, BDR. All right, that's it for designated routers. And now we'll talk about the different types of packets. Packet types in OSPF. In OSPF, there are 5 kinds of packets. The first is hello packet. and the second is database description. Third is link state request. Now fourth is link state update. The fifth is link state acknowledgement. Alright, these are the 5 types of packets that are used in OSPF. The first we'll look at is hello message. Hello is, as obvious it sounds, it's a greeting message. Routers use this to check, to communicate with other routers. Let's say here is a router and here is a router, and they both are linked, and for every 10 seconds, approximately 10 seconds, each router will say hello. This hello message is done so that hello, and this will also say hello, my neighbor is this guy, this router, something like that. This hello message is sent to check if the other router is alive. That is, if this router is reachable. If this router sends a hello and this receives it, then this will say that, okay, my neighbor is not dead, he's alive, I can reach him, something like that. So both routers will exchange hello, and that's hello message. Then the next type of OSPF packet is database description. We'll see what database is, what database it forms, or we'll discuss it now itself. What happens is, whenever this update is sent, right, each router will form its own database. Remember that in LSA, each router knew the whole topology, right? So what happens is, whenever there is information, each router will have a database called LSDB, link state database. Each router will have a link state database which says which router is reachable through which path and all things. So what is database description packet? Whenever a new router joins in, let's say a new router is joining in and it is connected to these networks, and it will say hello. Now this router is just connected, right? And these two routers have not seen this hello message ever. Now what they'll do is they'll send a database description packet, so that this router can have an idea of how the whole network structure is. Remember that this is not a whole database, but it is just a description of the database, so that this router will have better time figuring it out with other packets. So this is figured out using these two, link state request and link state updates. But this database is used as a it's like an introduction, so that it can know which router to ask for link state updates and everything. So it's like, let's say, yeah, when a new router joins in and it says hello, these routers will send the DB description so that this router can further construct its LSDB, link state database. All right, now for the third type of packet, that is link state request. In link state request, a router asks another router, give me the status of the whole network, and that will give, and the other router responds with link state update. And link state update packets, when received by some router, it will say link state, it will send another packet called link state acknowledgement. Acknowledgement is that, okay, I have received the update, thank you, something like that. Not thank you, of course they're routers. It's like, it's an acknowledgement that it has received the packets. So those are the 5 types of OSPF packets. Now we'll discuss a very brief way how OSPF works. First of all, what happens is they say hello and they send the database description, and then through link state request and link state updates, this router will figure out what the whole topology of the network is. Then what happens is it forms a database called LSDB, link state database, and uses Dijkstra's algorithm to calculate the shortest path and everything, and then routing happens. Yeah, that's for the basic working of Ospf. Let's recap it once. We were looking at Ospf. Ospf has one of the advantages that it can split the whole network into areas for easier management. And the routers which connect areas are called the backbone routers. And then we looked at something called neighbors. Neighbors are routers nearby. They communicate and test reachability with each other. And when they also form two-way linking, that is, each neighbor will acknowledge that he's a neighbor of mine, and they both will interchange packets frequently. Then we also looked at designated routers and backup designated routers. We saw that if each router forms a two-way linking, then that creates flooding and a lot of other issues. The network becomes congested with these packets alone. So some router will become a designated router so that flooding is reduced. The routers will acknowledge and form a two-way relationship only with the designated routers, and update packets from other routers are ignored. Then we looked at the type of packets in Ospf. There are 5 types of packets. There is hello packet. It is used as a greeting. It is to check if the neighbor router is alive, it is reachable or not. And if no hello message is received for some time, the router will consider that the neighboring router is dead. Then we have something called database description. If a new router joins in and sends a hello, then the router responds with a database description, so that it's like a description of the LSDB, and then link state request can be used by routers to figure out how the network topology is in the whole system. Then there is link state update packets as well. When there is a request, then there is an update, and once the router receives the update, it sends a packet called link state acknowledgement. And we looked at something like how it works. It receives the link state acknowledgement, it receives the link state update, and it constructs something called LSDB, and then uses Dijkstra's algorithm to form the routing table and for proper functioning. Alright, that's it for this video and Ospf. I'll see you in the next one. Thank you.